Hi, my name is Elrid Serrao, and I will be sharing my findings from Lab 3 Magnetic Field of Permanent Dipole Magnets. The goal of this experiment was to characterize the magnetic field of a bar magnet at different distances by using a magnetometer to measure the magnetic field while accounting for the magnetic field of the Earth. And from this, I found the magnetic dipole moment of my magnet to be 5.12 amp meters squared. We will be using an exponential equation to model the effect of distance on the magnetic field, and taking the natural log to create a linear model that we will use when plotting my data. Here, K is the magnetic moment times the magnetic constant, and we will be using the Biot-Savart law for a dipole with a magnetic moment to determine the magnetic field in our computational model. For the experimental setup, I began by orienting my table so the width of my phone, on which I am running the PHYS magnetometer app, aligns with east and west, and I determined the location of the magnetometer by moving my phone to find the max and mins of the X and Y magnetic fields. And then I took distance measurements of the points where the X component of the magnetic field reached certain values. And to end, I took measurements of the magnetic field at a distance 45 degrees off the axis of the magnet. Looking at my data for on-axis, I took the averages of my distance and magnetic field measurements and used the natural log to linearize them and give them a best fit line that we will use to determine n and mu. This is the data from my off-axis measurements, and it will be later compared to my computational model. And some things that I found is that the magnetometer reads 0 far away from the magnet, and that the X component of the magnetic field increases when the magnetometer approaches the magnet. Looking at my calculations and what my line of best fit is based on, we can see that my n is about -3 and ln of k is -14.471. Taking the exponential of this value gives k, and setting that equal to the magnetic moment times the magnetic constant gives us a mu of 5.19 amps meters squared. In my code, I begin by defining the magnet and its moment from my experimental calculations. And then I define a function to calculate the magnetic field using the magnetic field of a magnetic dipole moment that I showed earlier. Here, I define observation locations surrounding my magnet and use them to create R vectors, which I then use to call my function to determine the magnetic field at that location and make arrows showing the magnetic field at those observation locations. In a similar manner, I use my dperp to determine the magnetic field at the off-axis location. To end, comparing my off-axis results to my model, I found that my X and Y components were similar within range, and I am neglecting Z. And in response to my discussion questions, without orienting my experimental setup to north, the difference between my computational and experimental values would be greater because I would also have to account for the Y component in my linearization and calculations. And if I were to stick identical magnets together, because of superposition, I would likely get a reading close to double what I measured in this experiment. Thank you for listening.